Okay, so let's have a look at equilibrium. All right, equilibrium means our particle is at rest, if you like. Well, actually, the velocity remains constant. Okay, so if our velocity remains constant, it means that our particle might be at rest. Okay, or in fact, we have zero acceleration. So in equilibrium, a lot of the time means our particle is hanging suspended, stationary. Okay, so our acceleration is zero, or the sum of the forces is equal to zero. Or in fact, we have zero acceleration on the system, which means we have a constant velocity. Okay, so equilibrium could be either of those. In short, it means the sum of the forces is zero. All right. So, so for an object to be in equilibrium when two forces are acting upon it, the forces must be equal in size and opposite in direction. That sort of makes sense. All right. So we think about the reactionary force and the weight force. All right. Equal in size, opposite in direction. If we have three forces acting on it, we sort of access our vector knowledge a little bit here, and we think about the triangulation of forces. Okay, so if we consider this example here, we have three forces, F1, 2 and 3, just sort of colour-coded. If that particle is in equilibrium, all right, it means the three forces, when we align them head to toe, will form a triangle. Okay, in other words, the net force is zero. And that's the kind of scenario we have here. All right, that's how we might be able to align those forces, which means if we think about the angle between forces, all right, we've just got to be a little bit more clever here. If that's the angle there, theta 1, between the angle between the red and the green force, well, let's think about that force there. That angle, if you extend that line, is actually that one there, isn't it? So that angle in there is going to be 180 minus theta 1. Okay, so you've just got to think a little bit. Similarly, if we want to think about the angle between the blue and the red force, where does that angle match off? That's that angle there, isn't it? Okay, so again, that angle is going to be 180 minus that. And we can do something obviously between the blue and the green force, something similar. If I extend that green line through, that angle there is the same as that angle there. All right, so you've just got to think a little bit carefully when trying to determine the angle between vectors or angle between forces. All right, so let's have a look at some examples. Force of magnitude 2, 4 and 5 newtons acting on particle in equilibrium. To sketch a triangle of forces to represent the three forces. So if our forces are in equilibrium, that means obviously a particle is stationary. And so I've just randomly allocated the 2, 4 and the 5 Newton forces acting in those directions. Okay. Now the next part typically is to find the angle between vectors. All right. In this case, between the 2 and the 4. All right. So that's the vector theta there I'm looking for. If we go to the triangle that we create, that angle between the green and the red vector or red force, theta there, which means inside the triangle is the angle of 180 minus theta. All right, so once we've got three sides and an internal angle, we've got a cosine rule. All right, so if we just applied our c squared equals a squared plus b squared minus 2ab cos theta, our key sides, the 5 is opposite the angle, so they're the two that we have to make sure we identify correctly. And if we work through that process, cos of 180 minus theta, okay, puts us in the second quadrant where cos is negative, so we get a negative cos theta. If we go through that process, we end up with a 71.79 degrees. All right. Okay, so when we consider the tension of the string, I guess two things. One, the length of the string is not really relevant. Okay, the tension doesn't change at all. If we have multiple strings, we have multiple tensions. So if we have a different string, and that also involves if we have a string and a weight is tied to it, okay? If our weight is allowed to freely slide along the string, well then the tensions are the same, all right? So let's have a look at a couple of examples. So in this one here, we've got a 2 kilogram mass, okay? Is hung on a smooth string, so there's no friction involved. The string is 0.6 meters long and it's attached to a ceiling at points 0.2 meters apart. All right. So I've sort of got two diagrams here describing the scenario here. So there's our string 0.2 meters apart here on the left, which means each of the string lengths are 0.3 meters. Yeah. So using that information, we can see that we have a 1, 3, 2 root 2 triangle with a little bit of Pythagoras' theorem in there. So we've got two equal sides, so the two angles are going to be equal at the top there. So we have an isosceles triangle. So we can work out A, the dimensions of our triangle, and more importantly, the actual size of the angles that exist within our triangle. Okay, and that becomes important when we resolve our forces. So let's move into our actual force diagram. All right, so if we consider the forces in here, we've got our tension force acting at, so we've got our, let's undo that, maybe not. So we've got a tension force acting up there, and the same tension force is acting up the 0.3 meter strings. So the angles, using alternate angles, are both going to be the same size there. So even if you weren't sure if the tensions were the same, if we resolve parallel to the roof, okay, or horizontally, this component here, t cos theta, is going to be the same as the component going in the opposite direction, t cos theta. Okay, so the horizontal forces, because my particle is in equilibrium, are going to balance each other out. So the two forces are going to be the same. All right, which is what we expected. If we go to our vertical forces, I've got t sine theta plus t sine theta has to equal 2g's acting down. All right, so they're the opposite sides of the little triangle that we create. So in reality, we end up with 2t sine theta equals 2g. And if we if we solve for t, we get t is equal to g on sine theta. Now sine of theta from back over here, from that right angle triangle that we created, is equal to 2 root 2 on 3. So if we substitute that in, we get the tension is 3 root 2g on 4. Okay. Let's have a look at how example 2 changes, or example 15. Same sort of thing. Okay, we've got the same length of rope is used to support a 2 kilogram mass, tied 0.2 meters from one end. It will hang at different angles to the vertical if it stands at 0.45 meters apart on the ceiling. Okay, so again, we're 0.45 meters apart. One string length is 0.2, the other one is 0.4. If I bring that over into this triangle here, we can soon work out that that actually is a Pythag right angle triangle. So in actual fact, it is possible to determine that that angle there is 90 degrees, which might be useful when we come into another way of solving these triangles, which is called Lamy's theorem. All right. So I'm just going to label theta 1 as that vertical angle, theta 2 is that vertical angle up there, and there's theta 1 and theta 2. All right. So again, if we resolve vertically and horizontally, resolving vertically, so there's my sine theta 2, T1 sine theta 2, and my T2 sine theta 1, so the vertical components, both acting up, have to equal the 2g acting down. Horizontal, I've got T1 cos theta 2 acting to the left, and that's going to be the same as T2 cos theta 1 acting to the right. All right, so there's my forces in there. All right, now, at any point in time, I could substitute the thetas in, couldn't I? I thought initially we might just solve in terms of theta. So T1, if I rearrange, is T2 cos theta 1 cos theta 2. If I substitute that into for T1, so there's my T1, which is T2 cos theta 1 cos theta 2, into equation 1. It didn't become very tidy, so then just substitute in cos theta, work out cos theta 1, cos theta 2 from the angles that we've been given. And we soon find out that the tension in the string T2 is 8.75 newtons. Obviously, if I substitute the values then in for T1 over there, I can get the tension in string 1 is 17.54, which is maybe twice as much. So given it's the same string, string 1, T1 is getting twice as much force. It's taking twice as much force. So you might expect it to break there, I guess, initially. All right. What else have we got? We've got one end of a light string is being attached to point A. On a vertical wall, a mass of 5 kilograms is attached to the other end of the string. A force of P kilogram weight acts on the mass so that the string makes an angle of 30 degrees with the wall. Find P if the force acts horizontally. So that's diagram 1. The force is acting horizontally. We have a 30-degree angle. And again, we just resolve all our forces. So we see the little yellow triangle in here, where we've got our vertical and horizontal components of the tension. Yeah. So if I consider the horizontal forces, we're going to concentrate on A. The horizontal forces, all we've got really is PG is going to be equal to T cos 60, because it's the only forces acting horizontally. So there's that equation there. Undo that, highlighter. Vertically, I've got T sine 60 acting up, and that's equal to 5G acting down. Okay, so I guess it's fairly straightforward in this one. We don't have to worry too much with other components. So T, if we rearrange equation 1, the vertical component is equal to 10G on root 3. Substitute that in. So 10G on root 3 is equal to cos of 6 times cos of 60 is equal to PG. And so P is going to be 5 root 3 on 3. Okay. If we consider the second scenario here, my pulling force, P, is actually acting at right angles to the string. So we can see in here, so we've got two lots of components there we need to consider. All right, so again, if I resolve, which one's which? If I go horizontally, I've got PG cos 60 acting in that direction. I've got T cos 60 acting in the opposite direction. All right, so those two forces are equal. Similarly, if I go vertical, T sine 60 acting up plus PG sine 30 acting up has to equal the weight force acting down. So again, once we've got those two equations, if I work with my, so there's sort of equation 1 there. So we get root 3 on 2 PG equals a half T, so T is equal to root 3 PG. Substitute that into the vertical equations. Resolve and group terms together, and we can see there that P is going to be equal to 5 on 2. Okay, so once we get our equations, it's then just working on the solution or the solving the algebra of it. Okay, we don't need that. Okay, what we have got up our sleeve is a wonderful little theorem called Lamy's theorem, where if we do have that sort of triangulation of forces, like those strings and those sorts of things that we've got there, we can apply basically the sine rule to solve that situation. So what we're saying is, like in this example here, the P Newton force here over sine of the angle opposite it is equal to the Q Newton force over the sine of the angle opposite it equal to the R Newton force over sine of the angle opposite it. So that's really our sine rule. Okay, so when we have our, so if we, I guess if we consider example 17, which is like a triangulation of forces one, we can just instead consider, well, 10 over sine 120 is equal to P over sine 140, which is equal to Q over, well, what's that, 260, that's a 120 there as well, is it? 100, I should say, sine 100. So there's a set of equations there that we can just solve. So obviously I've got 10 over sine 120 is a complete ratio. So then P will be equal to that times sine 140. Q will be equal to that times sine 100. And you can compare those to the answers that we did previously. All right. Here's our little string sort of scenario that we've just been looking at. And again, once we've got our force diagram drawn, all we really then need to determine are the angles. Yeah, so if we think about, if I do a force diagram here, so if that's 90 degrees there and that's 90 degrees there, there's a little theta. So I'm saying that that's 90 plus theta. This one's 90 plus theta. And the one up there is going to be 180 minus 2 theta. So you could actually work out, because we've got the information from the string, we could actually work out the angles and put them in. But I thought if I just leave them in that form there, I've got the ratio then, 20 over sine of 180 on 20 equals, which one was T2? Is it the same string? This is 12 meters away between, that's the other end, joining the strings is only equal. Yeah, they are the same tensions. So I've called them T2 and T1, but obviously the angles are the same. So T1 is equal to T2. So, and we can see T2 over sine of 90 plus theta. Okay, so again, look, we just use a little bit of compound angle knowledge there as well if you wanted to. If you put the actual angles in, you could work out work it out on your CAS anyway. Okay, so you wouldn't necessarily need to worry about the double angle, compound angle, supplementary angle rules. All right, but you can see how instead of resolving horizontal and perpendicular, horizontally and vertically, Lami's theorem is actually quite nice. All right.